Hi, everyone. Welcome to Denoise. On this show, we talk about the latest AI/ML innovations, their implications, and their applications with the minds creating them. The innovation that we're going to talk about today with our guest Titouan Parcollet, who is a research scientist at the Samsung AI Research Center in Cambridge, in this paper, is an addition to summary mixing for automated speech recognition with streaming data with accuracy, less compute, and resource requirements. Where are we going to see voice assistants where we haven't seen them in the past? Maybe a surgeon's operating room, the next evolution of self-driving vehicles. I'm really excited to talk about this with Titouan. In addition to being a research scientist at the Samsung AI Research Center, he is also the co-leader of the SpeechBrain project in partnership with the University of Montreal. Titouan, thank you for joining us.
Thank you for having me. It's a pleasure.
So I would like to first ask you about the SpeechBrain project, if that's okay. Can you just share a little bit about what that is?
Sure. I guess in short, SpeechBrain is an open source conversational AI toolkit, which means anyone, researchers, teachers, companies can just use SpeechBrain to build speech technology. So it can be speech recognition, can be speaker recognition, something linked to speech synthesis, or trying to build also a conversational agent. License is Apache 2.0, which means, again, anyone can use it. It's free. Well, we rely on the community, so any help is appreciated here. But in terms of what you can do with it, as I said, so speech recognition, speaker verification, there are like dozens of tasks that you can do with it, basically. And it's one of the, let's say, the two biggest really open source speech toolkit, conversational AI toolkits. And others that exist that are at this size, usually they are owned by companies like NVIDIA and Meta, which means it can be a bit tricky to use it in a production scenario, for instance, which is not the case for SpeechBrain because, as I said, it's free and everyone can use it.
Very cool. And your interest in speech recognition goes back to your PhD. So can you share a little bit just about your journey with, or maybe further, but can you share a little about your journey to machine learning broadly, and then this area of interest that is speech
Sure.
recognition?
When I did my master's in Avignon, so I did my bachelor and master's in Avignon, deep learning was, at this point in time, it was not as huge as it is right now. And so basically I knew nothing about it aside from the mathematics, let's say, that are underlying to this field. So when I got offered to work on a PhD thesis that was about quaternion neural networks, so like hyper complex numbers neural network, I didn't know anything about hyper complex numbers and I didn't know anything about deep learning. So it was just super exciting. So that's why I got into this. But it means back then you could start a PhD in deep learning without any knowledge in deep learning and still, I guess, do well, which I think right now would be a bit more difficult to do this, a bit more challenging.
Right.
But that's how I got into deep learning with this. So I started, well, again, back then, nothing was, the only thing existing was TensorFlow, right? PyTorch was at the really, really beginning, for instance. So everything was much more simple, I would like to say, I think, than people that are joining now. So that's how I got into my PhD. And then, well, everything blew up because, well, I also got lucky during my PhD to do an internship with Yoshia Bengio at Mila at the moment where Mila exploded as well in terms of visibility and well, it just followed deep learning, right? So that was very exciting times where everyone was just super excited by everything, and it was way before the crazy hype that we have now. So after, of course, at the end of the PhD, we were already in the hype 3 years later, and then well, I did a postdoc at Oxford, and then became an associate professor in Avignon University, stayed for 2 years there, and finally 2 years ago now, I joined Samsung AI. So I left my tenured associate professor position in Avignon.
Okay. Very interesting. And to work on speech recognition.
Not only,
in
but
part.
yes. Yes.
Okay. And before we kind of get into the details of your paper, can you sort of situate us in the problem space? So, what's the motivation behind this work specifically, and what problem do you solve?
I'd say that efficiency for deep learning, so trying to find models that are quick to train, fast to infer with, that consume not a lot memory or just, let's say, constrained amount of memory, is relevant for any task, right? Like it's not only speech recognition, can be image classification, can anything. Efficiency is just important. So all this work goes into this efficiency scope already. It's just that we have expertise in speech recognition in my team, so we ended up applying to speech recognition this problem. But the idea is just if you want to have your speech recognizer on your phone. I mean, I'm working for Samsung, so I have to think about all these devices, right? Like phones, it can be your TV, it can be your fridge now, it can be many things, and you have very constrained resources there, right? Both in terms of like memory, storage for the size of the model, but also the compute resources that are embedded in these devices. And of course, you don't want the user experience of the smartphone to be slowed down because you're trying to transcribe something. Same for the TV and things like this. So constraint is quite strong. So efficiency is very important. So the whole scope is we want to do speech recognition or we want to do deep learning things that are on device, but we want to do it such that it is quick to use, cheap to use, and if we need to train them on device, for instance, then it's also fast to do and cheap to do it. Which also extend to if it's not on device, it also extend to cloud computing, right? Even if we are training our models in huge data centers, it costs money to do so. So you want to reduce the number of GPU you need, or you want to reduce the training time overall. It's also good for the planet, of course, less energy consumed. So yeah, it's the problem scope, like efficiency and doing things such that they train, infer quicker and cheaper as well.
Right. And obviously, always, like you mentioned, keeping in mind this is the consumer facing device, like user experience is equally, if not more important than some of the
Of
other
course.
things. So now, I didn't realize at first that this paper is actually kind of an extension, right, of a previous work. You and your team developed or introduced summary
Yeah.
mixing, which is what's built on in this paper.
Yes.
Can you, and is my understanding correct that summary mixing is an alternative to multi-head self-attention in the space?
Yes.
So can you tell us a little bit about what is summary mixing?
Yes, this paper is an extension of a previous one, which is often the case, right? You start with an idea and then you want to try it on different scenarios. But in short, summary mixing is indeed a drop-in replacement to self-attention, multi-head self-attention. Let's say self-attention for the sake of simplicity here. So it means any architecture where you have self-attention, in principle, you can just take this block out, so self-attention out, and put some remixing in place of it. And so depending on how it's implemented, since the source code is available, you can just, it's in PyTorch, the one we have, you can just take it and put it in your model and train. Input and outputs are the same. So main problem is self-attention has a quadratic time complexity, which is known. There are plenty of optimization out there now that helps with this. Can be flash attention, can be fast attention. I mean, you have plenty of alternatives that exist that tries to overcome this problem, but it's always around, which means if you have a very long sentence coming as input, which can happen with speech. I don't know if you want to transcribe 20 seconds of speech, for instance, or if it is like streaming speech recognition, you may want to have an infinitely growing amount of speech because the person will keep talking for minutes and minutes. So the sequence can get very, very long. So having this quadratic increase in complexity with the sequence length can be problematic. It's not necessarily problematic, but it can be problematic. So one of the solutions to this is either simplify self-attention or use it in certain ways that, let's say, are trying to avoid this quadratic complexity or to limit its impact. So you can have shorter sentences, you can do some trick in the model to change this. But usually if you do this, it will just alter the performance of self-attention. in the end. So the other solution is just say, okay, maybe we don't need self-attention, which is what we did with summary mixing. And we can go into the details of what led us to think this. But what we want to do is just remove it and do something else, because maybe self-attention is not needed. And this something else will have a linear time complexity, which is obviously much better when you have very long sentences, because your memory consumption, your inference time, well, the compute that are necessary will grow much more slower and with control, under control, because linear increase is much better than quadratic. And so summary mixing is just this, going from quadratic to linear time complexity, and it's a drop-in replacement to self-attention, meaning you can put this in any model. So any model that does speech recognition, or maybe large language models as well, but with some limitations, I guess. It will just work straight away.
And even though you introduced summary mixing in the previous paper, you do give a brief summary of it in this
Yes.
paper as well, just an
Yes.
overview. But the previous paper with summary mixing was for offline scenario, and that brings us to where we are here in this paper, where you're working on streaming
Yeah,
data.
exactly.
Give us a little bit of an overview of the
Sure.
paper. So, focusing mainly on the design, the experiment that you set up, and then the empirical performance.
Sure. Maybe I can do this like in as a form of small story, maybe, on how we ended up here with even summary mixing. So, as I said, we were interested in trying to reduce the complexity of our speech recognizer, because, well, the architecture that we may use for speech recognition and streaming, for instance, so you can use an architecture that is called transducer, so it can be a conformer transducer, but in the nature of it is already quite consuming in terms of memory and training time. That's just inherent to the architecture. So we would like to try and avoid wasting resources elsewhere. So that's why we started thinking about how can we make some components faster. And so we knew self-attention was a problem, so we got interested into this. And so the story is very short. I was collaborating with another lab, so it was EDIAP, basically, and the EPFL in Switzerland. And they invented what they called hypermixer, which is an extension of mixer, so MLP mixer. So we might not go into details of this here, but basically it's just also a replacement of self-attention that is linear in time complexity. And so we collaborated, and they just tried to put this into SpeechBrain, we talked about at the beginning, to do speech recognition. And at my great surprise, when I was collaborating with them, it was just working very well. So this linear thing that was much faster to train, cheaper to train, the self-attention, was working very well and very close to state-of-the-art speech recognizer using self-attention. So with that in mind, we just took this model, so hypermixer, and we started looking at the mathematics of it. And we ended up realizing this is just a sum operation. Like there is nothing crazy about it. The way it was presented was a bit fancy and in like deep learning terms, but in the end, if you just write the equation, these are just sums operation, just a sum. So we were even more intrigued, right? Like a sum is just working as well as self-attention, which is much more complex. And so this was actually aligning pretty well with the experience of another member of my team in Samsung, and also the literature, where it was shown that self-attention, once you train your speech recognizer, when it is fully trained and you look at the attention matrix and you look at how the attention weight are distributed, you can see that they spike a lot, meaning when the attention is focusing on the time frame number 100, then the attention will focus on this 100. Or with other architecture, it can be that they are pretty well distributed across all the time step of the sequence, effectively being just like a weighted sum as well, which all leads to self-attention might just be useless for speech recognition, because once trained,
Okay.
it is not used as it should be. Self-attention has been invented to do something, and this something is not used at all for speech recognition for some reason. And so that's why we just said, well, let's simplify even further hypermixer and based on this intuition. So we have a story of local relation and global relation that we want to map in speech recognition. So basically, what matters the most in speech recognition is to capture a local context. So this means if you are currently processing the time step 100 in your input sequence, what matters the most is like time step 99 and time step 101. It's not time step 1 or time step at the opposite of the sequence, right? So this means we need local relation. This is very important. And luckily, in speech recognition architectures, we usually use CNNs. So in the conformer architecture, we have CNNs that are absolutely perfect to learn this kind of very local relationship. So the only thing missing is the global one. So learning global relations in speech could be like noise, can be, I don't know, maybe speaker identity, these kind of things that are more distributed across the whole sequence. And very interestingly, if you don't have anything capturing this, it still works very well. By this, I mean, if you take a speech recognizer, a conformer, for instance, and you remove self-attention and you don't replace it with anything, so not summary mixing, nothing, you just train this model, it will work very well and like very, very close to state-of-the-art speech recognizer. We're talking about maybe a 0.3% absolute increase in water rate, so in reduction in accuracy. That's nothing, right? Well, the thing is, we still want state of the art. That's the point. we want the best performance, of course. So we need to introduce the global relationship mapping. But just to mention, this global relationship learning thing is not really important. It is if you want to reach state of the art, but you could even remove it and it works. And so this global relationship learning is where summary mixing comes in place. Before this, we were using self-attention, meaning we were using something pretty heavy in terms of compute to learn something that will give 0.3% improvement in performance, which is ridiculous somehow. So we need to come up with something much simpler. So we came up with summary mixing, which is just a sum. It's literally just a sum operation. So you can think of it as you have your input sequence that is like a sequence of frames because it's a speech. So in speech, we have like input frames, basically. It's the smallest tokens we can have here. And you will transform with a typical dense linear layer each time step independently. And then you just do a sum. So you reduce the whole sequence into a single vector. And this single vector, you can concatenate it back to the input, each input frame. And you just go to the next block. That's summary mixing. That's only a sum operation with a too dense layer in the middle. So that's still a few parameters to learn, but it's nothing fancy at all, just a sum. So very quick to compute, right? So in the first paper, we just do offline ASR, so non-streaming speech recognition, also spoken language understanding, I think. And so for this case, it just works very well. But we, of course, ended up asking ourselves the question, what if we do streaming? Because it's a sum, so can we play around the fact that it's a sum? Well, good for us, you can also just do a cumulative sum, right? So you just accumulate and it works just as well because, well, just adding new frames as they come is very simple in the end. And that's all you will do streaming summary mixing. It's just that, well, your input sequence is growing over time. So you keep adding new things to the sum before propagating.
In terms of the experiments, how did you set them up? What was the performance?
Sure. Well, luckily we have pretty standardized benchmarks when it comes to speech recognition that have been used for decades now, I think. Well, new ones are coming, of course, but the good thing is like all the speech researchers usually have in mind always the same data set, like Libre speech, for instance. Everyone will have this in mind. Even though now it's entirely solved, we keep using it. But we just use typical speech recognition data set like Libre speech and Vox Populi, for instance. Speech recognition in the wild is never clean, right? Like you always have noise in the background. People are talking with terrible microphones and things like this. But still, this is what we're using usually. And Vox Populi is, if I'm not mistaken, is like parliament speech. So it's also clean, but slightly less, let's say, than LibreSpeech. We've been using SummaryMixing with way more use cases where the data was much more noisy and things like this. But in the case of this paper, we just focus on this two, if I remember correctly. I think there is also Tedlium in the middle, which is a mix of TED Talks, which is, again, another acoustic environment. But this doesn't really matter. So that's the 3 data set we used. In terms of hours, it's fairly small for all of them. So none of them exceed 1,000 hours of speech for training, which is, by today's standards, very small, especially for industry standards. But even for the speech community now, we have like data set that goes up to 10,000 hours of speech, transcribed speech, because you need the label. And we had a lot of different scenarios, so we won't go through all of them. But let's say the main ones are, we want to compare SummaryMixing against self-attention. And the two things that we're interested in are, is it faster and cheaper? And is the accuracy that we obtain at the end, so the word rate, the same, at least the same, that's what we hope, because it's very hard to beat self-attention actually, or slightly better if we can. And so it turned out, when you use like a small toy task where you just give to the model sequences of increasing length, you can see, of course, very well self-attention, training time, and memory consumption follow like an exponential curve, of course. And you can see SummaryMixing staying linear with the increase in sequence length, which is what we expect, which is great, which means much less memory consumed and potentially training faster. What we've seen in practice, however, is that when you actually train, is that self-attention implementations right now, they are quite efficient in terms of compute time, like the way they are being computed. So in memory, it's still, let's say, much more consuming than SummaryMixing. So SummaryMixing enable people to use GPUs with reduced amount of memory compared to self-attention, for instance. But for training time, it is still slightly faster. So SummaryMixing is still slightly faster. I don't have exactly the numbers in mind anymore, but it's slightly. And when I say slightly, it's like it's significant in the sense you will feel it, but it's not like half the training time, for instance, maybe like 10 or 20%. I don't remember exactly. And the reason is the way the speech encoders are already reducing the number of time steps you have in a speech sequence. So the frequency of the speech encoder is quite reduced, meaning that below 30 seconds of speech, SummaryMixing is barely faster than self-attention. So if you go after 30 seconds, so that's true for a typical conformer architecture. They have an output frequency of 25 frames per second of speech. So it means if you have a sentence that lasts 1 second, you will have to process 25 frames. And so, well, multiply this by 30, you get the number of frames from which self-attention will start to be much slower than SummaryMixing. So below this, it is already slower, slightly, but it's not crazy. And 30 seconds of speech, it's already a lot. Like in most training data sets that we have, including LibreSpeech, Vox Populi, and Tedlium, sentences are much shorter, right? And in some data set, like Common Voice, which is also very well known, like the average sentence length will be around 5 seconds. LibreSpeech, I think it's around 9. So you can see that we expected it to be slightly faster during training, and it's the case, but it's not crazy faster. Memory consumption, however, is very different. So the story is slightly different for streaming, because using SummaryMixing enables something, I think, quite important. If you have in case of Samsung, you have Bixby or ASR, or taking notes, for instance. If you don't design things carefully with self-attention, well, Samsung designed this carefully, so hopefully it should not happen with their product anyway. But if you don't do this, then when transcribing, as you talk, the cell phone or the device will take more time to transcribe. So at some point, you will figure out that it's taking long to actually produce the transcription. To avoid this, most of the time, what we do is we remove the left context. So we load, we say, okay, this person is talking for 10 seconds, 20 seconds, 30 seconds, and then we stop, let's say at 30 seconds, we start removing the left information. So it means that we won't give to the model from second 0 to second 30, but we will give from second 10 to second 30 instead. And we will move like this. So which means we will have a window of 20 seconds. So no infinite left context, basically. That's the thing. And with summary mixing, because it's linear, the threshold before you have to do this is much longer. So in principle, this is what we say in the paper, with summary mixing, you can very easily use infinite left context when you are streaming, which give better performance, right? It will give you better accuracy rate of doing this. Like self-attention, if you use the full sentence length, you will get good water rate. If you start chunking, the water rate will go up and the accuracy will go down if you start chunking.
Now, I want to go back to the data sets a little bit because I'm really interested in this. So these are English data sets.
Yes. I think we might have in one of the paper, we have other languages as well, I think.
So would this change for other languages?
Nothing changed for other languages. So that's a good point. Because summary mixing is like, as I said, task independent somehow. It's just you change. So in speech recognition, what we have usually is the speech encoder, and then we have different ways of having decoders. And so the choice of decoder may change if you do multilingual speech recognition, for instance, or if you do monolingual speech recognition. But the speech encoder, usually, the architecture stays the same. And that's where we use some remixing. So whether it is French, Italian, and I think these are the languages that we used with Common Voice, like French, Italian, and Dutch. And you don't have to change anything. Just use some remixing like for any other language. And of course, it's not like language specific, let's say.
Okay. Now, this is a little bit outside of this paper, but I'm thinking you're on the phone, right? This is the kind of stuff that you're working on. What about slang? How do you train different accents, different words used in, British English, American English?
Sure. So this is more linked to adaptation, which is, of course, very important for all the companies that are doing speech recognition on the on device. So it can be Samsung, Apple, anyone is facing these issues. And this is linked to adaptation. So let's say for the biggest subset of this, so American accent, British accent, the good thing is like this, hopefully, companies will have data sets internally that will integrate all these specificities, right? So they might have thousands of hours of American English, thousands of hours of British English, thousands of hours of Australian English. And so in the end, after training, all this will be fixed, let's say. Now when I say fixed, it's like it will just work the same across all the board, hopefully. Usually it's slightly different because in practice we may have more American English data than British accented data. So a few biases like this can happen. But then what you need to do is adaptation. And so this is not linked to big subset like British English or American English, but more like the way one person is talking. So his personal accent, his or her personal accent. But also, as you said, like words that might be pronounced in their own way, let's say. And so then comes on-device adaptation, and this is a very different topic. It's not linked to the architecture. These are different techniques where it's actually quite hard to do because the key problem you have here is that you don't have the transcription to do this, right? You don't have any labels. So you know potentially that this is always the same speaker talking, but that's the only thing you know, right? You don't know what he's saying or what they are saying. And you don't even know what is the sound in the background, if it's a car, something. And so then you have to deploy a few techniques to adapt to this scenario, which is complex. This is very hard because you have usually very few data. First, that's the first thing. Like when someone talks to Bixby or Siri or whatever Google Assistant, it's not like you are actually storing everything on the phone. So it's not like the phone will hold 1 hour of you talking with Siri or of Bixby. This is not happening, right? And so it means we have very few data, and so usually it might happen overnight, where we just have 1, 2, 3 sentences to train on, which is ridiculous, right? Like if you compare this to the hundred of thousands of hours that are necessary to train a model, and here you just have like 3 seconds. So it's very hard to do this.
That's interesting. So I guess that kind of brings me to sort of the big question is how does this work relate to voice assistants? Does it make them better, and how does it affect the user experience?
Yeah, I mean, so things are changing a bit now because everyone is trying to turn voice assistant into this speech LLMs things with large language models, right? As
Right,
we've
right.
seen with Gemini, ChatGPT, all the things. So let's say this in that way. Wherever you have a speech encoder, which means you need to take as input a speech sequence and produce a new sequence of something. So it can be text in the case of speech recognition, but it can be also just a latent representation in the case of large language model, for instance. Anytime you need this, which is the case for any conversational assistant, basically, any smart assistant needs this, you can just use summary mixing instead of self-attention in there. And so this means your smart assistant should have a reduced latency. And also, because of the use of summary mixing, the footprint in terms of memory, so maybe the cost, the overall cost of the hardware cost of the assistant will go down. Or if the memory doesn't
Mhm.
change, it means maybe it will be able to do more things in parallel, concurrently, because the speech recognition parts take less memory. But the most important part for the user, the thing that should be felt, is the reduction in latency, right? Like when you talk and you get the
Right.
feedback directly.
I mean, seconds are a problem
Exactly.
anymore. So tell me, who should read this paper? Who would find it beneficial or find it interesting?
Well, that's an excellent question. So I think this is interesting. So at least intriguing. That's the point. So there are different people. The first ones are people that are not necessarily linked to working in speech. So I
Right.
said speech recognition, but we tried, as I said, spoken language understanding. We tried self-supervised learning for speech. We tried things that are linked to speaker recognition. It always worked. So people that are intrigued by the fact that something as simple as a sum can replace self-attention should have a look, because that's to us, that's the
Okay.
intriguing part. And the interesting part is, like, we've been doing all these complex things for 10 years, I don't know how long, and no one even realized that it's useless. So that's the interesting thing. So
Right.
anyone intrigued by this would be interested by summary mixing, I think. The other set of people, of course, is people interested in speech recognition in general, or speech. So we have one in self-supervised learning as well. So this is like a quite hot topic. And all the people that just don't have the resources to train models on hundreds of GPUs, or don't have GPUs with a lot of memory to train their models, will have a look at summary mixing, because the code is, again, available. So, well, license is non-commercial, or, well, contact Samsung if you want to use it for a commercial purpose, because it's patented. But for research purpose, for instance, well, you can just take the code. It's ready for SpeechBrain, so you can already press the key and it will work on SpeechBrain on different tasks. So anyone intrigued, and so, as I said, the people intrigued by this, not necessarily speech, and the people that are doing speech and don't have a lot of resources. But I guess even large companies might be interested in not spending, like, when you have thousands of GPUs, a 10% reduction in training time is massive, right? So yeah, I think all these people's, basically.
Right. Yeah. No, I think it's really interesting that it's not domain, it's not domain specific. So people could kind of see where it could fit for
Yeah,
them.
well, there is still
Um,
limitations to summary mixing, but
mhm.
that, for instance, for language modeling, it could not work depending on the place. Well, again, we could discuss about
Okay.
why and what is the intuition behind this, but for anything related to speech, it will work. I think image as well. For language, it might be a bit more complex.
And so we already talked about how this is an extension of a previous paper. So what's next? What's the future work for this?
Good question. Well, this is not on me. Let's say it's more on
Okay.
Samsung and what Samsung wants to do with this. I think we've done what we wanted to do with summary mixing, because so we started with just offline ASR and we added spoken language understanding. Then we pushed this to streaming ASR. And the last thing we wanted to try that we were interested in was self-supervised learning, where we usually have these huge models. So training time is very important here. You have models that have billions of
Okay.
parameters, which is absolutely not the case for speech recognition. And so we have covered all the things we wanted to try. So I think the next thing would be maybe a paper wrapping up everything with a bit more experiments,
Hmm.
a bit more details and things like this, maybe, because that would close our line of work on this somehow. Then what is the
Right.
next step for SummaryMixing? This, well, I don't know. And I guess even if I knew, I couldn't tell.
We can okay, that's fair. And what about for you specifically? Is that it might be the same answer, but what are you working on now? Do you have anything, any research papers coming up, or anything we can look forward to
Uh,
from
yeah,
you?
well, this is also very hard to answer without spoiling anything.
Okay.
I think there are quite a lot of different interesting areas for speech in general. So everyone now is being driven by this generative AI things. This is, of course, impacting speech recognition as well, or self-supervised learning and things like this. As I said, because we see this big push of ChatGPT, Gemini, where we have this smart assistant that are just LLMs with an interface with speech. So this is one of the different areas that can be of interest for me, and the reason is like everyone wants to do this, so we have to investigate this properly and see if it's suitable, see if it's better than what we have, see if we can do a product with it. I mean, there are so many questions open, and this is not just Samsung, of course. Like um, I guess people at Apple are also wondering if they can use it. And I mean, right? We saw all this announcement this year of these companies about Gen AI. So of course, Gen AI for speech, well, it exists as well, and we will have to follow this. But for myself as a researcher, I'm still interested in efficiency, and I still think there are quite a few things that are still not done right, and that's the way I work. And this is why it was like this for some remixing. We spotted something that was not looking right. We were spending too much compute to do something, and so other problems exist that are in the same state. Like, why are we even doing this? And so I guess I will keep working on this. And it's related to speech in general. And of course, I mean, this I can say, SpeechBrain, big things coming. Well, I communicate a lot about SpeechBrain because it's already open source, so it's much easier in terms of IP and stuff, of course, than what we do at
Right.
Samsung.
What you're allowed to say.
Yeah. So,
Right.
well, what I'm doing at Samsung, you will potentially see it in keynotes or blog
Well,
posts or things like this. Yeah.
yeah, we'll find it out
Yes.
eventually. Okay, great. Thank you so much. I appreciate your time.
Thank you. It was great.